Hi guys, Daniele here. Today we continue our series of tutorials on databases and we talk about queries. Queries are a way to make requests to databases, which then in turn gives us back the answer to the request we made. Uh, Possibly the most common usage of the queries is to filter out tables according to some properties of the entries. So only get some entries and not all of them, or to order the entries according to a certain property. To start, let's rebuild the database of the last time we used the Tix-Mono folder and we analyze it by centroid, loudness, and spread. It's just an example. You can do it with your own database. If you had saved it, you can read it back by using the read message, or you can click on the button and it's going to be analyzed and it's going to be filled. Let's verify that. It's okay. Then, how do we perform queries with dada.base? Well, we do that by using a query message. And the query message has to be followed by the actual query we want to perform. And the syntax we are using is the SQLite syntax. So this is not something that is only applying to dada.base. It's a very general syntax for any SQLite database. We are just going through some easy examples in this tutorial, but just know that you can do much more than that, and please refer to the online tools, and there are a lot of good online tutorials on this. The simplest query you can perform starts with the select keyword. The select keyword selects some entries or some properties of the entries and gives us back those properties from a given table. The easiest one you can imagine is select asterisk from samples. This just selects any column from the table samples. So this is going to give us any column of every entry in the table samples. And we are just going to post it in the max window with bach.post at max depth 1. So we have every entry posted out in a different line. It's convenient to use bach.post for that. But this is not something we use most of the time. This corresponds to some sort of dump of the table. We are dumping all the content of the table. Every element, every entry has its own line and all the columns are there. But we can just retrieve some columns from the table. For instance, with a select file name from samples, we're actually only retrieving the file names for every entry in the table samples. And you see we just have that. Or if we use select file name comma type from samples, we are getting the file name and the type from the table samples. Again, every element will show up, every entry will show up, but just the file name and types are going to be output. Please notice that the comma has a special meaning in the max message. So whenever you want to use it literally, you have to escape it. So we put a backslash before that in order to use the comma properly. Instead of outputting the file name and type symbols, you can avoid that if you don't need that by turning off the output call names attribute. And in this case, the query we just performed has the same output values, except there's no longer the file name and samples router before the actual content. This may be useful in some cases if you just want to have the content and you know that the first one is a file name and the second one is a type. Another thing you can add to your queries is the distinct keyword. How does that work? Well, if I remove the distinct keyword and just perform a query like select type from samples, what I get is for every element in the samples table, it's type. So type low, type mid, type mid, type mid, type mid, type mid, type high, and so on for every element. Whereas if I add the distinct feature, I only get the distinct types which are embedded in the table. So just 3 of them, type low, type mid, and type high. This may be useful in some cases. But another thing you can do with the select keyword is to add a min or max keyword, asking for the minimum and maximum value of a certain field. In this case, we are asking both the minimum value of the centroid and the maximum value of the centroid inside the table samples. What we are gonna get is a response of the kind, you can see it in the max window, mean centroid 483, max centroid 7742. So we can retrieve them with bach keys, and we have the minimum and maximum value of a column inside our table. This may be useful if you, for instance, want to normalize something according to them. Please notice that min centroid and max centroid are symbols, so the parenthesis is embedded in the symbol. It doesn't represent a level in the LLLL structure. It's part of the symbol. Another thing you may do instead of min and max is count. Count returns the count of a given column. The most common usage is to count how many samples IDs are there, because we know that sample IDs are unique IDs that are assigned to any entry of the table. So if we count them all, we know how many entries in the table there are. In our case, there are 163 entries, and so we can do a little bit of max logic and obtain a comment where the number of entries is displayed. This might be useful in some cases if you want to display how many entries your database has. One other thing you may want to do is to have your entries ordered by a certain property. So, for instance, here we are ordering the output by the centroid. So we are spitting out all the file names in the table samples, except that they are ordered by centroid. The first one will be the file name with the lowest centroid, and the last one will be the file name with the highest centroid. This is convenient in some cases. We can verify that if we also output the centroid along with the file name. So let's clear the max window and do that again. And you can see that the first one has a low centroid, and then they go up until the last one having the highest centroid. If you want to sort them in the opposite direction, so from the highest to the lowest, you can add a desc keyword at the end. This closes the ordered by clause and means that the ordering is not performed in ascending order, rather in descending order. And this is convenient in some other cases. Here you go. This is the highest one, and this is the lowest one. You can use other kind of functions here instead of a simple name of column. Random is one of those functions, so we can get all the samples in the table, but ordered by a random order. This is convenient many times. Or we can just want to limit the output to a certain number of elements. Imagine you just need the 5 loudest entries in the table, and you don't want to have all of them. So there's no point in putting dada.base into the trouble of getting all of them and outputting them. So you can use the limit keyword. The limit keyword is a SQLite keyword that just outputs a certain number of entries you asked. In this case, we are outputting the 5 loudest elements in the table, and we can also output them with their respective loudness. You can couple this with a little bit of max logic to retrieve all the file names, for instance, in one list, a flat list, and all the centroids, for instance, in another list, sorted by centroid. This is kind of easy. You can see this is a small example where we take file names and centroid. Those are going to be output without any keyword, which means that I'm just going to have couples of file name centroid, file name centroid, file name centroid. If we transpose it, we just have a list of file names and then a list of centroids wrapped in a level of parentheses. We pick each one of them and we print them out. So we have the list of centroids, they are in ascending order as expected, and the list of corresponding files. Some of the time you need to only retrieve a group of entries that match a certain property. It's not like using limit where you get the first n entries. You only know the properties they have to match. For instance, you want to know the file names of the samples whose type is low. And you can do that via the where clause that accepts a condition to be matched. In this case, we are combining the request with a little bit of audio. We are taking a random output from dada.base and we are opening and playing it. So here we are playing one random low sample from our dataset, and you can hear it. Or we can play a random high sample in our dataset, and so on. On integer and floating point columns, we can use inequality conditions. For instance, we can search for entries whose spread is less than 0.7. Here they are. There's just one of them, apparently. Or we can combine conditions with logic operators, such as AND and OR. Here we search for a high entry whose spread is also greater than 0.85. Here's a bunch of them. This can be combined with the other keywords we have used, with the other clauses we have used. For instance, here we take the file names from the entries inside samples, but only when the type is high, and we order them by centroid, and that's the answer. Or we could do something more fancy, and we can also put a select keyword inside a select keyword. This is something a bit more advanced that you can do with SQL queries. We're selecting the file names from the table samples where the centroid is less than a quarter of the max centroid we find in samples. So you have to think that this keyword will return the maximum centroid that will be found in the sample. It will be used here instead of this parenthesis and multiplied by a quarter. This will be our limit for the centroids of the elements that we are looking for. And then we are ordering the elements by random. And that's the answer. There are not a lot of them. There's just 3 apparently. Let's give a last examples of usage. And these examples of usage may stem from a consideration. We have seen that in our dataset, we have arranged the elements by type. We have given 3 labels, low, mid, and high. But actually, we just have 5 low elements. We can see that if we count the sample ID when the type is low. We have 107 mid elements, and we have 51 high elements. That's not really balanced. We might want to balance it out in order to have more or less the same number of mid, high, and low elements. So we need to change a little bit the threshold for high and low. How can we do that? Well, one way of doing it is to get all the centroids from the table, flatten them out, and use bach.quantiles. If we do that and remove this cable for a little while, well, we have 2 values, and those 2 values are the quantiles, the 1/3 and 2/3 quantiles in our table, according to the centroid column. What it means is that the centroid of 1/3 of the items is going to be below this value, and the centroid of 2/3 of the items is going to be below this value, which means that we can actually use a bit of a more advanced query, which is not a select query, but it's an update query. And the update query changes some columns inside our dataset. And how does it work? Well, what we do here, we update the table samples, setting the type as low, where the centroid is less or equal than the first element we are inputting. So in this case, 2915. And then we are giving another query. Notice that this comma is not escaped, so those are 2 different queries. We are updating the table samples to set the type mid, where the centroid is between the first and the second value. And notice that we are using the between keyword to do that. And then there's one last query. We update the table samples to set the type as high, where the centroid is greater or equal to the second element coming in. So if we do that, we have actually updated all the type columns in order to match the new repartition. And we can verify now that we have 54 low elements, 54 mid elements, and, well, 55 high elements. It's not a multiple of 3, so we don't get a perfect repetition, but you see that's as close as we can get. Again, if you want to save your dataset, don't forget to use write or write.txt to do that. This is all for today. I hope this was somehow informative, and stay tuned for the next part.